All right, welcome to day 6. Rather than just having you check your answers on the front here, we're going to flip through and talk about each of the problems. So in 16, we want to do limit comparison. We wanted to compare to 1 over 3 to the n. The original and that are both greater than 0. When you divide those and do our limit as n approaches infinity, you'll get infinity over infinity. So take your derivative using L'Hopital's, that's 3 to the n times natural log of 3 for both top and bottom. Those divide out, so our limit approaches 1. That is a finite positive value, meaning our original series does the same thing as our nice one we picked. Well, our series of 1 to infinity of 1 over 3 to the n is the same as saying 1/3 in parentheses raised to the n. That's geometric. The absolute value of r is less than or equal to 1, so it converges. Therefore, we can say by the limit comparison test, our original series converges. For 18, remember we always want to, or in general, we do 1 over n raised to the difference in the powers. So there's no degree in the numerator, and a square root of n squared is like a degree of 1, so we want to use 1 over n. Both that and the original are always greater than 0. So when we divide those and do the limit as n approaches infinity, we get 3 to the n over square root of n squared minus 4. Well, that limit should be the same as the limit of 3 to the n over square root of n squared, because when n goes to infinity, the minus 4 is not going to do anything. Well, square root of n squared is absolute value of n. Absolute value of n as n goes to infinity, n will be positive, so we can think of it as just n. 3 over n divided by n is just 3, so that's a positive finite number, meaning our original series does the same as our nice series. Our nice series, you can either say it diverges because it's the harmonic series, or you can say diverges since it's a p series where p equals 1. Therefore, by the limit comparison test, our original series diverges. For 19, there's a gap in 3 between our degrees, so we want to use the series of 1 over n cubed. Both those are always positive. When we divide them and do the limit as n goes to infinity. Same degree, so the ratio of the leading coefficients is 2/3. That's a positive finite number, meaning our original series does the same as our our nice series. Our nice one is a p series with p greater than 1, so it converges. Therefore, by the limit comparison test, our original series converges. For 21, if you distribute the bottom, you'll have an n squared, so the gap in the degrees is 1, so we want to use 1 over n again. Both of those are positive. When you divide it and do the limit as n approaches infinity, your leading coefficient ratio will just be 1, which is a positive finite number. So that means our original series will do the same as our nice series. Our nice series, again, was the harmonic, which diverges, or you could say it diverges because it's a p series where p equals 1. Therefore, by the limit comparison test, our original series diverges. In 23, we can think of the square root of the n squared part being like an n times n is n squared, so our gap is 2. So we'll use 1 over n squared as our nice series. So the limit, or both those are greater than 0. Our limit as n goes to infinity when we divide them will be the same as if we had n over absolute value of n. And where that's coming from is you can divide one of the n's out. So then you have n over your square root. As n goes to infinity, the 1's not really going to do anything. Square root of n squared is just absolute value of n. But when n goes to infinity, it's going to be a positive, so we can think of it as n over n, which is 1. That's a positive finite number, so our original series must do the same as our nice series. Our nice series was a p series with p greater than 1, so that converges. Therefore, by the limit comparison test, our original series converges. In 24, our n's already have the same degree, but we've got an extra 2 to the n minus 1 on the bottom. So we want to, in this case, do 1 over 2 to the n minus 1. They're both going to be positive, so when we divide them to our limit as n approaches infinity, the 2 to the n minus 1's divide out, then your ratio of the leading coefficients is 1, so 1's a positive finite number. So therefore, our original series does the same as our nice series. Our nice series can be rewritten as 1/2 in parentheses to the n minus 1, which is geometric. The absolute value of r is less than 1, so it converges. Therefore, by the limit comparison test, our original series converges. In 26, we want to think eventually when n goes to infinity, that second part will be a square root of n, which is just n, so we'll have 2n on the bottom. So the degree difference is just 1, so we'll do 1 over n. When we divide and do the limit approaches infinity, eventually we'll have 5n over 2n when we do like the square root of n squared is the absolute value and then make that an n. So the ratio is just 5/2. That's a positive finite number. So the original series does the same as our nice series. We've got p series where p is equal to 1, so it diverges, or you could have said it's the harmonic series, so it diverges. Therefore, our original series diverges by the limit comparison test. 27 is not really a normal pattern like the other ones. So we're going to use 1 over n as our other one. When we divide them, don't do a keep change flip. Leave it as sine 1 over n over 1 over n. Well, when n goes to infinity, that's the same as if we rewrite our limit, and let's say x goes to 0 of sine x over x. Because when n goes to infinity, both the 1 over n's are going to go to 0 anyway. Well, limit as x approaches 0 of sine x over x is something we've seen a bunch before. That's just 1. So that is a finite positive number. So our original series must do the same thing as our nice series. We have harmonic again, which diverges, or you can say p series where p is equal to 1. And therefore, our original series diverges by the limit comparison test. All right, these next groupings, you had to use one of each of the options there. Now, there's 8 questions and 7 options, so one of them will end up being used twice. So I'll show you the options I use. There might be scenarios where you could have done some of the others, but remember you had to use each of them once. So if we neaten up our original fraction there, we just get 1 over n to the 1/2. So you can think of that as a p series with p equal to 1/2, so therefore it diverges. So that checks off our p series one. 30 is a geometric. The absolute value of r is less than 1, so that converges. 31, you can compare that to 1 over 3 to the n. 1 over 3 to the n will always be greater because the denominator is bigger in our original. 1 over 3 to the n can be written as 1/3 to the n, which converges by a geometric because p is less than 1. Therefore, because 1 over 3 to the n was always greater and it's converging, everything smaller than it must converge. So our original series converges by the direct comparison test. In 32, I used what we saw a lot of in this homework assignment, the limit comparison test. The difference in our degrees is 2, so I used 1 over n squared. When you divide them, you have ratio leading coefficients. So you have 1/3, which is a positive finite number. So therefore, our original does what our nice one does. 1 over n squared is a p series with p greater than 1, so that converges. So therefore, our original series converges by the limit comparison test. In the next one, limit as n approaches infinity of our terms is 1/2. So therefore, that diverges by the nth term test. Remember, if your individual terms do not go to 0, then that's automatically diverges by nth term test. And that's usually the first one you want to look at and see, because that's a quick one. In 34, if you write a couple of your terms, you get a 1/2 minus a 1/3 minus a 1/4. If you kept going, you'd have a 1/4 minus a 1/5, and so on. So notice a bunch of those are going to wipe out. That's our telescoping. So as n goes to infinity, you're going to have your first term minus the last term. So 1 over n minus 1 over n plus 2. Well, as n goes to infinity, that second thing will go to 0. So this is just going to converge to a 1/2. And you would say because it's telescoping. For 35, I chose to use the integral test for this one because it is positive, it's continuous, and it's decreasing. So limit as b approaches infinity, you got your integral from 1 to b. We had to do a u substitution with a 1/2 correction. Your antiderivative was negative 1 over u, or negative 1u to the negative 1. Then fill in. I changed my bounds to match my u's to be 2 to b squared plus 1. So if we go back up here and sub the b squared plus 1 and the 2 in, as b goes to infinity, that first fraction is going to go to 0, so you'll have a half times a half is a fourth. So this converges by the integral test. Remember, an important thing with the integral test is all it tells us is it converges, because it went to a finite number. Our series does not necessarily converge to 1/4. The integral test just tells us that the series does the same thing as the integral does, so we just know the series converges, but not necessarily to what number. For 36, I had used up all of my options, so I could use any one I wanted, so I just did limit comparison again, compared to 1 over n squared. You got 3 when you did your ratio of the leading coefficients. 1 over n squared p series p greater than 1, so it converges, therefore the original series converges by limit comparison test. And the last one, it said if you have two series and the terms in one series are always smaller than the terms in the other, and if the small one converges, then the bigger one has to diverge. Well, that's not necessarily true. Think of 1 over n cubed and 1 over n squared. 1 over n cubed will always be smaller than 1 over n squared. 1 over n cubed converges because it's a p series with p greater than 1, but the 1 over n squared will also converge because it's the p series with p greater than 1. So that statement they made is false. All right, so that was kind of a lot of homework problems to talk about, okay? Because you have to write your reasoning and show everything with these problems tend to take a little while. Today's topic is the alternating series test. So the alternating series is nice in that it's pretty easy to recognize when you might want to use it. So there's two examples of alternating series there. Alternating series, we mean that the signs are alternating. So you could have a negative 1 to the n, which would yield the first term being negative, and then it would switch signs after that. If you have negative 1 to the n plus 1, you would get the first sign to be positive. Now that's if n equals 1. Now a less common alternating series, you could see like some n equals 1 to infinity, and you could have sine of, let's say, 2n plus 1 pi, we'll say. So the 2n plus 1 will make sure that we always have either a 1 or a negative 1. And then you could have some other stuff after this too. But like when you sub in 1, you would get, sorry, and I would want this, sorry, I want that over 2. So when you sub in 1, you'll get 3 pi over 2. When you sub in 2, you'll get 5 pi over 2. When you sub in 3, you'll get 7 pi over 2. So those are all the odd pi's over 2 for sine. So that means you have either 1 or negative 1. So that could cause it to alternate signs as well. Less common. Usually you just see negative 1 raised to a power. So here's an example of an alternating series. We have negative 1 to the 1 to start, so we're going to go negative, positive, so on. And then this is just geometric. You're multiplying by a half. If we go down to the bottom, we'll look at the alternating series test. You want to look for this anytime you see you have an alternating series. An alternating series will converge if these two things are true. So if the next term is always less than or equal to the term that came before it. Now, that might not be true right at the beginning. So we say n is greater than some m, saying if that's eventually true. So if the first couple terms, they aren't getting smaller each time, but eventually they do, then that's okay. So as long as the next terms are smaller than the previous term. And then the second one is as n goes to infinity, our terms have to go to 0. Now, the second one makes sense because if it wasn't going to 0, we would be diverging by the nth term test. So if your second one fails, we definitely know it diverges. Now, when we say an and an plus 1 for these, we're thinking of the absolute value. We're ignoring the negative signs when determining if one is smaller than the previous one. So for this one, we're going to see if it converges or diverges. We want to recognize we've got that negative 1 there. So this is an alternating series. So if we write out a couple of terms, we're going to have negative 1 over 1. Then we'll have plus 1 over 2, negative 1 over 3, plus 1 over 4, dot, dot, dot. So is each successive term less than or equal to the one before it? Yes, so that checks out. And does our limit of 1 over n go to 0? Well, it does. So we would say, therefore, by the alternating series test, our original series, n equals 1 to infinity, of negative 1 to the n times 1 over n, converges. Now, usually you'll have to write these. Okay, these first couple, we're having it right for you just so you know what to think about. But normally for an alternating series test, you will have to actually write that. So here's our next one. We got the negative 1 to the n, so we want to think, oh, that's alternating. Let's think alternating series test. Let's write out a few terms. Our first one's going to be negative. When we put in 1, we're going to have 1 over 2 minus 1, so that's 1 over 1. When we put in 2, that's going to be positive, and we'll have 2 over 3. When we put in 3, we're going to have negative 3 over 5, and so on. So is each successive term getting smaller? Well, that's like a 1, a 0.6 repeating, a 0.6, so it does appear that it is. And does our limit go to 0? Well, notice same degree, so it'd be ratio of leading coefficients. So this is no. Our limit as n goes to infinity of n over 2n plus 1 is equal to 1/2. So therefore, we would say that our series n equals 1 to infinity, negative 1 to the n of n over 2n minus 1 diverges by the nth term test. So if you get one of these 1 or 2 to fail, that doesn't tell you that it diverges on its own. You should never be saying diverges by the alternating series test. The alternating series test can only show you convergence. If it's going to diverge, we would have to be able to then show by some other reason that it's going to diverge. Now, another option you have for showing that each term successively is going to get smaller is you could take your an values and think of them with x's in there and do the derivative. So here's a quotient rule. You've got derivative of the top times the bottom minus the top times derivative of the bottom over the bottom squared. Well, that neatens up into something that's always negative. You got negative 1 over something squared. So that tells us there that it's always getting smaller. So that would be if it is tough to determine from the terms, you could always do it that way. So, for example, what if you had something like this? It's going to be an alternating series, but subbing in numbers, you might not know what ln of your different numbers are. So imagine we took the derivative of n over ln of n. So we would have derivative of the top times the bottom minus the top, and I'm just doing them as x's, just keep in mind. Well, this would be ln x minus 1 over ln of x all squared. Well, notice the denominator is always positive because it's squared. And eventually, natural log of x gets bigger than 1. So this will eventually always be positive. This was our derivative, so that means eventually our terms will always be increasing. So this would tell us that we couldn't use the alternating series test. We would have to look for something else. Um, Likely you would probably want to um, show it with the nth term test that it will diverge. You could do limit as n approaches infinity of n over ln of n, get infinity over infinity, do your derivatives, and go from there. Another way to think of it is natural log grows really slow. Natural log looks like that. N is like y equals x. It looks like that. So your numerator is going to grow a lot quicker than your denominator. So that's another way you can determine that alternating series test would not be available here. So we've got a negative number raised to a power. That's going to lead to an alternating. If we look at our terms, we've got 1, 1, like 0.75, a half, 5/16 is less than a half. So yes, it looks like this is getting smaller. But our value is definitely approaching 0. Well, remember, don't worry about the negative. Let's look at limit as n approaches infinity of just the n over 2n to the minus 1. Well, initially we would think of that as infinity over infinity, so we can do L'Hopital's. So that would be 1 over your derivative of anything that is a to a power is it times natural log of its base. And then we technically have to do a chain rule here. So we'd have 2 to the n minus 1 times ln of 2, that's our basic derivative rule, times derivative of the exponent, which just happens to be 1. So that doesn't, the chain rule doesn't really affect anything. Well, now the denominator is going to keep getting bigger, but the numerator is staying at 1, so that's going to go to 0. Another way that you can think of it in your head to justify it is an exponential is going to grow a lot faster than a linear. So that could also tell you that it's going to approach 0. So this one does check out. So we can say, therefore, by the alternating series test, our sum of n equals 1 to infinity of n over negative 2 to the n minus 1 converges. Okay, let's imagine 1 and 2 weren't written there, because I want to show you what you would do like on a homework problem. So the first thing, you would recognize it's alternating. Okay, let's check our two things. So you would write an plus 1 less than or equal to an. We would look at it and see, okay, it looks like they're getting smaller. So usually what I do is I'll put a little check mark there. And then I'll say limit as n approaches infinity of an equals 0. And I'll go to look at that. Okay, well, as we see over here, the denominator is going to get huge. The numerator is going to stay the same. So yes, that works out. So therefore, we can say the series n equals 1 to infinity of negative 1 to the n plus 1 over n factorial converges by the alternating series test. So that's it for the alternating series test. We saw with the integral test that there was a remainder that we could find. Well, there's also a remainder for the alternating series as well. So with an alternating series, S is representing here the infinite sum. the infinite sum can be made up of a partial sum, so meaning the sum of a first set number of terms, plus the remainder, so the leftovers. So if you put the partial sum and the remainder, which would mean everything else going to infinity, that should give you the infinite sum. So if we think of this, that means if we took our infinite sum and subtracted off our partial sum, that should give us the remainder. Well, our remainder, or the leftover, should always be less than or equal to whatever that next term is. And let's think about why that is. Let's say on a number line, there's our infinite sum. Well, let's say right now our partial sum is like right here. And let's say our next term is a positive term. Well, that positive term, what it's going to do is it's going to overshoot the infinite sum because you will have added too much. Well, then the next term is a minus. So you're going to add on a negative, but the absolute value of it is not going to be as big. So when you add on that negative, that's going to bring you back to here. And then you'll add on a positive that wasn't as big as that negative, so that'll bring you to the other side, but not as far away. So as you keep adding successive terms in an alternating series, it bounces back and forth on either side of the infinite sum, but it keeps getting closer and closer and closer. So we know that next term is going to either add or subtract, depending if it's positive or negative, and take you further on the other side of the infinite sum. Well, because it's going to take you further, we're guaranteed that the remainder, the amount that would take us to exactly that infinite sum, has to be less than it. So we know that our remainder will always be less than or equal whatever that next term is. And that next term will always be easy to find. So keep in mind when we say a sub n plus 1, we're saying that without the sign. So in this one, if we wanted the sum of our first 5 terms, the next one here, so we had minus plus, so we would have a minus 1/5. Well, we could think of this as negative 60 over 60 plus 30 over 60 minus 20 over 60 plus 15 over 60 minus 12 over 60. The negatives would give us negative 92 sixtieths. The positives would give us 45 sixtieths. So this would then give us minus 47 sixtieths for our fifth partial sum, our S5. So that means our fifth remainder should be less than or equal to the absolute value of the sixth term. Well, our sixth term would just, our last one was 1 over 5, so when we sub in the next number, we'll just have 1 over 6. So we know then that this is within 1/6, or I should say the absolute value of the distance between that and the infinite sum is 1/6. So really what we know is that if you have your infinite sum here, it has to be between negative 47 sixtieths minus 1/6 and below negative 47 sixtieths plus 1/6. And it's one of those options because we did the absolute value. So when you do an alternating series error, you know your remainder is less than or equal to the absolute value of the next term. So our last thing for today, we've got this series here, and we want to find the partial sum that is within 0.001 of our infinite sum. Well, it's an alternating series, so we want to think alternating series remainder. So the absolute value of our remainder should be less than or equal to the next term. So what we want to know is we want to know when is the next term less than or equal to 0.001. Since the next term is always the remainder, that'll tell us when we are within that amount. So what we're going to do, remember we ignore the negatives, we really want to know when is 4 over the quantity n plus 1 factorial going to be less than or equal to 0.001. This will tell us the value of n, whose next term is less than or equal to 0.001. And all we're going to do is graph this on the calculator in a graphs page. We've just got to put the n in as x. So we're going to have 4 over x plus 1. Factorial is down with the question mark. And hit enter, and then do a control T. So we're going to scroll through and find the first one that is less than or equal to 0.001. Now you need to be cautious because they will switch to absolute or to scientific notation eventually. So look at the bottom and when it's highlighted and watch out for the e's. So there's 0.005, that's still too much. Now notice it switches to 7.9, but it's e to the negative 4. 0.001 is the same as 1 times 10 to the negative 3. So because that's to the negative 4, that's like saying 0.0007. So that is smaller than 0.001. So n equals 6 is the first one that would work. Now, what I would want to see like on a test, so our answer is n equals 6. What I would want to see on the test is like the last two lines in the table. So we would have 0.0007 dot dot dot, and I think our one before that was the 0.555. Yeah, 0.00 and then 5 repeating. So I would want to see those last two rows to show, okay, yeah, 6 is the first one where it is less than or equal to 0.1. So the alternating series test and the alternating series remainder are very powerful tools that we will see quite a bit. Have a great rest of your day.